Okay, hi everyone, welcome back. Welcome to November, all right. And remember your right to vote. Tomorrow is obviously election day. All right, so today is, okay, well, it's week 12. Today is Monday, November 2nd. Election day is tomorrow, November 3rd, all right. Now, we actually started lesson 28 last time, day 21, before Halloween, all right, happy Halloween. So I'm going to start with a review. I'm going to start with a review video. I'm going to start with a review video for lesson 28, review some ideas there on confidence intervals for means, where sigma, the population standard deviation, is known. And then lesson 29 deals with the case where the population standard deviation is unknown. That's the more practical case, but since I want to go over the theory and the ideas a whole lot, I'll spend a lot more time covering 28, although 29 is more practical. All right. Also, I finally get time to grade homework this week, finally. All right, that'll help a lot. And also, I wanted to ask the question, what are your thoughts about Discord? So just for a moment, because I heard students tell me that Discord was a good place for students to have forums to talk about things like homework questions. And in fact, I heard that students use Discord more often than they use Canvas, actually. So were there any thoughts about that? You can go ahead and unmute. Any thoughts about using Discord maybe, as opposed to Canvas for a place for student interaction or student forums? Any thoughts about that? Really? Have you used Canvas? Have students used Canvas, Discord, other? Okay, so what are pros and cons of Canvas? What makes Canvas good or bad? I've seen instructors use Canvas, but gamers, the students who play video games, they use Discord, and that's become very popular at Mesa, I've heard. Yeah, any thoughts? Okay, any thoughts about Canvas or Discord? Okay, so Canvas has been nice, but doesn't prompt open discussion. Yeah, and Pronto's part of Canvas. Okay, so yeah, because remember, I did have a I do have Canvas open for student discussion. People haven't used that yet, so don't forget that I do have my Canvas shell open and available for students. So if you wanted to discuss amongst each other, or if you had questions, you can use that. I heard that Canvas was used mostly for students to check their grades, but the people who use Discord told me that Canvas was mostly used to check grades, and that they found Discord to be very helpful for things like mutual interaction. That's what I heard from them. Yeah. All right. But anyway, we can go ahead and talk more about that later. All right. Okay. So in the meantime, any questions before we go on? Any questions before we go on? All right. So yeah, different thoughts here. Okay. So let's go ahead and go on. All right. And let's continue. Rules. Rules. In lesson 28, estimating a population mean mu if the standard deviation sigma was presumed known. That was the less realistic case, though. So remember, we're trying to construct things like these, right? A confidence interval for a population mean. It's centered at the sample mean, x bar, and the margin of error is the half width of the confidence interval. So we're saying that the population mean mu could be at the sample mean x bar, give or take the margin of error. So in this case here, we could say 74, give or take 4 points for this confidence interval up here. 74, give or take 4 points. Or write out the confidence limits explicitly, 70 points, comma, 78 points. So we're estimating a population mean mu. We're giving an interval estimate, a CI, for a population mean mu. We're assuming for now sigma is known. Not realistic, but at least we can use the z distribution for this stuff. And we need the central limit theorem to apply, meaning the big daddy distribution is about normal or the sample size is large enough. So we don't necessarily need normality at the beginning. Remember, eventually, even with non-normal big daddy distributions, averages eventually get about normal distributions for large sample sizes. Well, under those conditions, here's our confidence interval for mu. It's the sample mean, give or take the margin of error. The margin of error is determined by this critical value. The confidence level, if it's bigger, it makes this thing bigger. And this is the standard error from the central limit theorem for a mean. So in the next video, I'm going to review the 95% confidence interval we developed last time, and we'll go on and construct a 99% confidence interval afterwards. So let's, any questions? Again, I'm doing a review here, and I'm going to review the example we did last time, but feel free to put questions in chat. Hi, everyone. Let's review our example 1 here, where we constructed a 95% confidence interval for a population mean. So we want a CI, a confidence interval, for mu. And it's going to be centered at the sample mean x bar. All of our confidence intervals for a population mean mu will be centered about the sample mean x bar. So in example 1, we said that a machine was designed to make cartons of 16.0 fluid ounces of ice cream. So we want these kinds of cartons of ice cream. The amount of ice cream in the cartons is approximately normally distributed, which means that we can use what theorem? We can use the CLT, the central limit theorem. If the big daddy distribution is assumed normal, then we can use the CLT. If not, then we better rely on a large sample size. And we're going to assume that the cartons are going to have a population standard deviation of 2.35 fluid ounces. So we're assuming that sigma, the population standard deviation, is known. We're going to assume that sigma is known, which is why we're applying the methods of this lesson. Because if sigma is presumed known, then that means that we're going to use the z table or the z distribution. Because we want to find a confidence interval for a population mean, we're assuming sigma is known, and the CLT applies. So we're going to use a standard normal z distribution. And then here are the sample statistics, which we're going to repeat later on. We take a random sample of 19 cartons. So little n, the sample size is 19. The sample mean, that's our value for x bar here, is 17.2 fluid ounces. And based on all of this, we found, in example 1, a 95% confidence interval for this population mean mu. Remember, the sample mean is x bar, the population mean is mu. And we wrote the CI, the confidence interval, in different forms. So when we wrote out the confidence interval, we got 17.2 fluid ounces, give or take 1.1 fluid ounces. So the population mean mu, we believe, is the sample mean, x bar, give or take this margin of error. If you work these limits out, then we can write this confidence interval in actual interval form, where we have the lower limit, where we subtract the margin of error from the sample mean. 17.2 minus 1.1 was 16.1 fluid ounces. And then the plus case, we need a plus sign here, 17.2 plus 1.1 was 18.3 fluid ounces. And again, that was our 95% confidence interval for mu. And it was centered at the sample mean. But that was for a 95% confidence interval. What if we were to construct a 99% confidence interval under the same circumstances? Would our 99% confidence interval be wider or thinner, smaller? Would it be wider or thinner or smaller? Which would it be? Well, how would the confidence interval be more likely to contain this population mean, mu? And like all confidence intervals for mu, it needs to be centered at the sample mean. Well, to be more confident that this interval will contain the true value of the population mean, we need it to be wider. We need it to be bigger. So how can we construct this 99% confidence interval? And how would this be different from the 95% confidence interval? How would the result be different? Well, it's going to be a wider confidence interval. And how will this work be different? Okay, so in example 2, we're going to look at a 99% confidence interval, CI, for this population mean, mu. And again, we're going to assume that the population standard deviation, sigma, is known. This might seem like the less realistic case. I understand that. But we do get to use the z distribution in this case. In the next lesson, we'll discuss the case where the population standard deviation is assumed unknown, which may be more realistic. Okay, so we're going to repeat example 1. It's the ice cream carton problem. But this time we're going to find a 99% confidence interval, CI, for this population mean, mu. The population mean amount of ice cream per carton. In your final interpretation, you should write this out, what mu stands for. Because if you just tell a layperson, oh, mu is between this and that, the layperson might go, what is mu? Because that is literally Greek. All right. So we're going to write the confidence interval in 2 different forms, like we did before. In this form, where the population mean is expressed as the sample mean, give or take the margin of error E. And this interval form here, where we actually work out the lower limit and the upper limit. And then we'll interpret the confidence interval. We're going to use this hint, well, these hints from the z distribution, the standard normal distribution. Although if it came right down to it, you could figure these out using online software or tables. All right, let's do this. Let mu be the population mean, here the population mean amount of ice cream per carton. It's good to declare what mu is. The methods of this lesson apply. Again, like in example 1, why is that? Because, going up here, back in example 1, the methods of this lesson apply because we're finding a CI for a population mean mu. We're not doing a CI for sigma or P, for example. We are assuming that the population standard deviation sigma is known, which is a bit weird sounding, but we're going to run with this in this lesson. We're going to assume sigma is known. And we're going to assume that the CLT applies. We know the CLT applies here because we're assuming that the Big Daddy distribution was about normal. If we were to look at these various cartons of ice cream, we're assuming that the distribution of these ice cream amounts is normal, or about normal. So the methods of this lesson, lesson 28, they will apply. All right, same cast of characters regarding the sample statistics. The sample size n equals 19 because we sampled 19 cartons and found out how much ice cream was in these 19 cartons. The sample mean, if you take the 19 cartons, you take the amounts of ice cream, put them in an Excel worksheet, for example, or maybe a calculator. If you work out the sample mean, we get 17.2 fluid ounces. X bar. We're assuming the population standard deviation is assumed known. Sigma is 2.35 fluid ounces. Maybe this is on the label, on the side of the machine. the standard deviation is 2.35 fluid ounces, and you have a 25-year warranty, a guarantee that that will not change. We're only concerned that maybe the average amount of ice cream might be changing. So a recalibration might be necessary in that sense. All right, so we have these sample statistics. The 19 may well be predetermined, actually. We have values for n, x bar, and sigma. Now you could calculate the sample standard deviation S, but in this lesson that's irrelevant. We're assuming that we know what sigma is. So we don't care if the sample standard deviation is 2.25 or 2.45. Now if it turns out the sample standard deviation is way off from this, if S turns out to be 10 fluid ounces, then you might question this assumption. Okay, we have different tests for that, finding out if sigma might be legit, this value here. All right, so the margin of error, this would be given to you on homework or exams. The margin of error, well, you can use it on homework. On a test, this would be given to you on a formula sheet. The margin of error is given by this critical value, this positive critical value from the Z distribution. So for a 95% distribution, the CVs, the critical values, were at 1.96 and negative 1.96.
Over 95% confidence interval. Right.
In general, they'll be at Z sub half alpha and its opposite. Now, the hints I gave in the homework, they're consistent with these comments over here. If you're doing a 99% confidence interval and the Z distribution is involved, then you're going to want these critical values, positive 2.58 and negative 2.58. They'll be opposites. They'll be symmetric about 0. That will always be the case if we're constructing a 99% confidence interval and we want to use the Z distribution. And we're dealing with these two tails here. All right. So once again, using the hints, which I just showed you over here, we want to use these critical values, these CVs, positive 2.58 and negative 2.58. The positive 2.58 is your Z sub alpha over 2. That was that fancy notation. It represents the positive critical value. Finding my thing again. Okay, over here. In the generic notation, Z sub alpha over 2, that positive critical value. It's going to be different between a 95% confidence interval and a 99% confidence interval for Z or for any distribution. Okay, now, this is one case where our work here is going to be different from what we saw before. So how is this different? In fact, to really emphasize this, I'll put this in purple. Put a big arrow here. Whoops. I just want to circle this, the 2.58. Because for the 95% confidence interval, okay, the positive critical value was only 1.96. So we ended up with a smaller margin of error. This time, we're using a larger critical value. 2.58 is a larger positive critical value. And we have the same values for sigma and n as we did in example 1. Sigma is still 2.35, n is still 19. So if you round off the margin of error to 1 decimal place, remember we round off to the same number of decimal places as x bar was given to. X bar was given to 1 decimal place. The margin of error is about 1.4 fluid ounces. Remember that if you want to be conservative, you could round up. So if this were 1.41, we could round up to 1.5, but I'll accept either. Here, we get 1.4. Actually, let's take a look on Excel. What would we have gotten? 2.58, 2.58 times 2.35 divided by the square root of 19. Yeah, 1.39 something, that rounds up to 1.4. So whether you round off or round up, you're going to get 1.4 as your margin of error. And that's different from before. The margin of error before in our 95% confidence interval was bigger. It was smaller. I apologize. It was smaller, 1.1 fluid ounces. The margin of error then was smaller. The margin of error now for the 99% confidence interval is larger. It's 1.4 fluid ounces because the critical value here was larger. Okay. So to find this form of the confidence interval, we're saying the population mean is given by the sample mean, again, the 17.2 fluid ounces, give or take the margin of error, which is now 1.4 fluid ounces. It's bigger than for the 95% confidence interval. Okay, so we take the lower limit and the upper limit. We obtain these by taking the minus case and the plus case. The minus case and the plus case. From the minus case, we get 15.8 fluid ounces. From the plus case, we get 18.6 fluid ounces. So our 99% confidence interval for mu is this interval from 15.8 fluid ounces to 18.6 fluid ounces. Before, it was smaller. It was 16.1 to 18.3 because the margin of error was smaller. This interval is wider, and it's, again, centered at the 17.2 fluid ounces. The interpretation is, it's the same as before, except that we have 99% here. We are 99% confident that this interval contains the population mean amount of ice cream per carton, basically mu. We don't want to write mu out to a layperson. We are 99% confident that this interval contains the population mean amount of ice cream per carton. So in terms of your business strategy, again, observe this is wider than what we had before. What does this analysis suggest that the ice cream company do? So you have the option of recalibrating the machine or not. And maybe it takes some money to recalibrate the machine. It probably will take some money. Will it be worth it? Well, we're trying to get 16.0 fluid ounce cartons of ice cream. The thing is, this 99% confidence interval is saying that it's quite possible that the population mean is 16.0 fluid ounces. And the fact that our sample mean was a bit high, 17.2 fluid ounces, that might be chalked up to sampling error. In fact, the 99% confidence interval is open to chalking that up to sampling error. It could be the case that the population mean for the machine is actually 16.0 fluid ounces, but this is due to sampling error. And maybe the machine doesn't have to be calibrated. This discrepancy could be due to sampling error. The cartons are supposed to contain 16.0 fluid ounces of ice cream, and the 99% confidence interval we have here for mu does contain 16.0 fluid ounces. It's between 15.8 and 18.6. Based on this analysis, the ice cream company has insufficient evidence against the claim that the population mean is 16.0 fluid ounces. So if a company rep for the machine comes by and says, don't worry about it. What you're seeing, we can chalk it up to sampling error. Your sample mean here, given your standard deviation, assuming our sigma is correct, okay, you're getting a sample mean of 17.2 fluid ounces. We can chalk that up to sampling error. Well, we, the ice cream company, okay, we have insufficient evidence against the claim, against that machine representative's claim. So we're not ready to sue them. We're not ready to recalibrate the machine. Or maybe it's not necessary. Who knows? Maybe the company might want to do it anyway just to be safe. But according to this statistical analysis, it's not imperative. It's possible that mu is in fact 16.0 fluid ounces. And what we're seeing in our sample can be chalked up to sampling error. That's possible. It's quite possible. There's insufficient evidence to suggest the need to recalibrate the machine. Again, this 99% confidence interval is wider than the 95% confidence interval. So we have greater confidence that this contains mu. However, you could say that this examination is less powerful, literally less powerful, in the sense that if the machine really does need recalibration, perhaps 99%, that's being a bit too liberal with how wide this is. 95% is the gold standard, but this is a bit subjective. What confidence level do you use? As an instructor, I'd have to give it to you, and you would work it out. It comes down to interpretation. And as for a business strategy, that may go beyond math and statistics. But hopefully, it'll be informed by statistics. Next time, let's say that you're going to conduct a study. How many people or how many cartons of ice cream do you need in order to get the kinds of results, the kind of confidence interval and precision level of confidence interval that you're looking for? Next time.
Now, before that, I do want to go back to it was the 95%. I want to go back to the 95%. Way back here. Okay, so this is our 95% confidence interval. Now look at this 95% confidence interval. 16.1 to 18.3 fluid ounces. Now, if that's our 95% confidence interval from you, all right, well, let's say the machine rep says, hey, actually the mean is 16 fluid ounces. According to our confidence interval, what do we say to the machine rep? The machine rep says the mean is 16 fluid ounces. We're getting this is our 95% confidence interval for the population mean amount of ice cream per carton. What do we say to the machine rep? I think there might be a problem. Why might there be a problem? Where's 16.0? Is it inside or outside this confidence interval? It's outside. So it might be kind of freaky, but according to the 99% confidence interval, we have insufficient evidence against the machine rep's claim that the mean is 16 fluid ounces. Here, we would have sufficient evidence against the claim. So you can see the confidence level can affect the interpretation and our company's policy. So again, this is something that freaks math professors out. Different confidence levels can lead to different conclusions, and that can freak people out. 16 fluid ounces outside this interval, we have a problem with the machine rep, right? Whereas the interval we got here for 99%, 15.8 to 18.6, 16.0 is in here. Then it's possible that we're okay, that 16 ounces could be okay. That is actually the mean. So that's kind of weird. Be prepared for that. All right, going on.
To read what you're looking for. Next time. Hi, everyone. We're now going to look at the issue of determining a sample size n before you even conduct a study. So before we draw a sample, it would be nice to know how large the sample size should be so that we have a certain confidence level and a certain margin of error E. So let's say that we want to predetermine both a confidence level, which is typically predetermined, but also the margin of error E. So we're going to select the sample size so that we can pre-select the margin of error. We can do that, assuming that we have a good value for sigma, an accurate value for sigma, which we'll talk about later. So determining the sample size little n for estimating a population mean mu. How do we figure out a sample size so that we can get the kind of confidence interval that we want in terms of its overall properties? So for a 1 minus alpha confidence level, so remember some common confidence levels are 95%, like 0.95, or 99%, like 0.99. For a 1 minus alpha confidence level and the desired margin of error E, the required sample size little n is given by the following formula. Of course, you won't have to memorize it. It'll be provided to you somewhere, like here, if you're doing homework. Now, you might be wondering what this operator is, this pair of symbols over here. That's the ceiling or round up operator. So for example, let's say that this stuff in the middle, let's say that this argument in here, the stuff in the middle is 899 on the dot, 899 exactly. Well, if that's the case, there's no rounding to do. You just grab the 899 as your sample size. So if this over here, if this piece in here is an integer greater than 30, because remember, we would like the central limit theorem to kick in. Where we're not sure if we're going to have an initial assumption of normality. So it would help a lot if this were to be greater than 30. So if the integer is 899, we just grab that integer as our sample size. Now, if you get let's say 899.1, something like 899.1. Well, this operator, this pair of symbols here, will tell you to round up. So round this up. That's what the ceiling or roundup operator does. Round up to 900, the next integer. Again, that's a way of being conservative, playing it safe. When in doubt, to play it safe, make the sample size just a tiny bit larger. Don't go nuts. Don't make it 1,000 or 2,000. Then you're going way beyond what's required of you. Be reasonable. Okay. Now, why do these pieces make sense? Well, what are some factors that will, literally some factors that will make the sample size larger? Well, the confidence level has an impact on what critical value we use. So for a larger confidence level, the larger critical value we use in here, and then the larger a sample size we'll need. So if you need a higher confidence level, you would expect to need a larger sample. Also, if the population exhibits more spread, then we're going to need a greater sample size to accommodate that. So if the population is more spread out, we're going to need more people or more ice cream cartons in order to adjust for that. So for example, if you have a very varied classroom of students, they're not just all coming from the same high school, for example. If you have a very varied classroom of students that come from many different high schools across the state, and it's a college class, then you may need a large sample size to accommodate that greater variability. But then, look here, the margin of error down here is in a denominator, and the larger the margin of error is, the smaller this will be. And the smaller the margin of error this is, the larger this will be. So if we want a smaller margin of error, if we want to shrink E, the margin of error, we need to raise N, the sample size. And bear in mind, this is all squared. So the impact is even more powerful than without the square. Math people might say that the sample size required varies inversely with the square of the margin of error. It's an inverse square property. Don't worry about that. All right. As I said before, it helps if this is greater than 30. But if it's not, then in order to use these methods, the original distribution better be approximately normal. So we have to add in that condition. All right, that's so that the CLT applies. If the sample size is big enough, if it's beyond 30, then we don't really have to worry about that normality issue. So let's do an example. All right, so in our example 2, our 99% confidence interval for mu looked like this, from 15.8 fluid ounces to 18.6 fluid ounces. That was a confidence interval for mu, where mu was the population mean amount of ice cream per carton. Okay, now notice that this interval is 2.8 fluid ounces wide in terms of the width of this interval. So the margin of error is half the width, or 1.4 fluid ounces. The overall width is 2.8. Half of that, the margin of error, is 1.4 fluid ounces. But let's say that we want to come up with a sample size to shrink the margin of error down to 0.5 fluid ounces. So we want to go now from a margin of error of 1.4 fluid ounces now to a margin of error of 0.5 fluid ounces. Let's say we're going to conduct a similar study tomorrow, like as a verification. What sample size would I need? So I'm going to replicate this experiment, but I don't want a confidence interval with a margin of error of 1.4 fluid ounces. I want to set the sample size little n. I want to determine the sample size little n, so I'm guaranteed a margin of error of 0.5 fluid ounces, assuming that I want, again, 99% confidence. A 99% confidence level. And we'll interpret the result. It turns out that, again, for the 99% confidence interval, it helps that we're going to use 2.58 as our positive critical value. Because 2.58 and negative 2.58 will trap 99% of the Z distribution in the middle. That's a given hint. Okay, solution. Use the formula that I just showed you. The 2.58, the positive critical value, goes in here. The population standard deviation, we assume that was known. If it's not, then I'll show you ways around this. But 2.5 fluid ounces, we're assuming that that's known. The desired margin of error for the confidence interval, 0.5. That goes in the denominator here. And again, this fraction is squared, which tends to amplify the effects of these parameters. So we have 2.58, the positive critical value. Sigma is 2.35, that was given, over the desired margin of error, 0.5. You take that fraction, work it out, and then square it. Now that turns out to be 147.04, and even though this is really close to 147, remember, these symbols here tell you to do what? They tell you to round up to the next integer. That's to play it safe, to be a bit conservative. Or emphasis. So 148 cartons of ice cream. If we want to be guaranteed a 99% confidence interval from you, where the margin of error is 0.5, so it's exactly 1 fluid ounce wide total, right? 1 fluid ounce wide total. 0.5 is the half width, the margin of error here, right? We're going to need about 148 cartons. We need to randomly sample, here's the interpretation, we need to randomly sample 148 cartons of ice cream to be 99% confident that the eventual sample mean will be within about 0.5 fluid ounces of the population mean, mu, the population mean amount of ice cream per carton. I'm saying here the eventual sample mean because we don't know it yet. We haven't conducted the study yet, so we don't have a sample mean yet. But we're setting things up. We're arranging it. We're not cheating because we're using legitimate statistics. It's just this time, instead of being given n and finding e, we're doing the reverse. I'm pre-specifying a desired value for e, and now we're finding the value of n, the sample size we need to accomplish that task, under 99% confidence. Next, we're going to talk about how difficult it is to reduce the margin of error, and it's harder than you might think. I'll give you a hint. It's because of the square. Next time.
And that's going to be a really key point. Questions so far? Questions so far? Feel free to put questions in chat. All right.
Hi, everyone. We're going to talk about how difficult it is to reduce E, the margin of error. Now, don't say it's because stats class is hard. It's not. And it really comes down to this formula here. This is our formula for the required sample size if you want a certain margin of error E, given a confidence level, like 95%, or in this case, 99%. Now, take a look here. In example 3, we needed a sample size of 148 to get a confidence interval, a CI for mu, the population mean amount of ice cream per carton, that looks like this, where when we eventually construct the CI, the confidence interval, it's a 99% confidence interval, by the way. If you take a sample of 148 cartons of ice cream and you do your statistical analysis, you find the sample mean, all right, you find the sample mean, then when you construct your confidence interval, it's going to look like this, where the sample mean is, of course, at the center of your confidence interval for mu, whether it's 99% or something else, and the margin of error is the half width of this interval. Now remember, in the previous example, we were looking for a margin of error of half a fluid ounce. So in order to get this kind of confidence interval, we needed to sample about 148 cartons of ice cream. Our sample size, little n, required, had to be at least 148. If it's bigger than 48, then you'll shrink the margin of error even more.
148.
Remember our interpretation from example 3. We need to randomly sample 148 cartons of ice cream to be 99% confident that the eventual sample mean, whatever sample mean we get for those 148 cartons, will be within about half of a fluid ounce, 0.5 fluid ounces, of the true population mean amount of ice cream per carton. Okay, so the required sample size was 148. Now, what if your CEO for this ice cream company, it could be Ben, maybe, it could be Jerry, but let's say, or someone else, let's say the CEO for this company says, hey, for this study, I'd like to have a smaller, more precise confidence interval. Why don't you cut the margin of error in half? Now, if your CEO just says that off the cuff, then your CEO may not have taken statistics or may not have done well in statistics because it's harder to reduce the margin of error than it looks. Even at the same confidence level, here, 99%, what sample size would we need to cut the margin of error, E, in half, down from 0.5 fluid ounces to 0.25 fluid ounces? That is from half a fluid ounce to a quarter of a fluid ounce. Well, here's a clue. When you take this formula for the required sample size, little n, let's actually bring in the squares here, right? A mathematician or a physicist might say that there's an inverse square relationship. Don't freak out about that, but there's an inverse square relationship between n, the required sample size, and E, the desired margin of error. So if you want to cut the margin of error in half, some people might guess, oh, do you just double the sample size to maybe about 300? No. In order to cut the margin of error in half, it's not enough to double the sample size. You have to quadruple it. You have to multiply it not by 2, but by 4 because of this inverse square relationship. Well, this is right here. Right. If you want the new margin of error to be half the old margin of error, like in this example over here, from 0.5 to 0.25 fluid ounces, the sample size n would have to be multiplied not by 2, but by about 4. Granted, there are rounding issues over here. So in example 3, given the same specifications, if you wanted the margin of error to be cut in half down to 0.25 fluid ounces, your sample size would have to grow from 148 up to 589, which is about 4 times as large as before. If you want the new margin of error to be 1/4 of the old margin of error, then the sample size, little n that's required, it's not multiplied by 4, it's multiplied by the square of 4, 16. If you want to reduce the margin of error down to 1/10, you need 100 times the sample size. So it's much harder to reduce the sample size than you might think.
Reduce the margin of error.
So if your boss says, hey, why don't you just cut the margin of error in half?
I should emphasize, you want to reduce the margin of error, it's hard. If you want to reduce the margin of error, it's harder than you might think.
Your sample size has to grow. It's got to be multiplied by about a factor of 4. Warning, it is more difficult to reduce the margin of error E than one might think. The sample size has to grow a lot.
Next time, we'll talk about another issue with this formula. It's a key structural issue. What happens if we don't know a value for sigma? That's a big question. I'll address it next.
Okay. Any questions thus
Wait a
far?
minute.
Okay.
Hi, everyone.
Any questions thus far? Any questions thus far?
We're taking another look at
yeah.
this sample size formula here. And a key question is, well, hey, what if I don't have a value for sigma? What can I do?
Okay, let me restart this. There we go.
Hi, everyone. We're taking another look at this sample size formula here. And a key question is, well, hey, what if I don't have a value for sigma? What can I do? What if I don't know the population standard deviation? Now, a clever student might say, well, hey, why don't you just use the sample standard deviation? But here's the problem. Wait a minute. Literally, wait a minute. What's the purpose of this formula? We're trying to determine a sample size for when we conduct a study later on. We haven't conducted the study yet. We haven't done our survey yet. We haven't touched these ice cream cartons yet, or we haven't called up these people yet. So we haven't done the survey yet. We don't have a sample yet. We don't have a sample standard deviation yet. So what can we do instead? What can we plug in for sigma? Our estimate for the population standard deviation. Well, there are various remedies. And although this is a big question, it's not a big question on your homework or exams because I won't push you on this issue on homework or exams, but it's an issue worth exploring. How would you estimate sigma for that sample size formula? Well, we could try to use the sample standard deviation, little s, from a related study. So for example, let's say that we're interested in doing a study of American men, some characteristic of American men. Well, we might turn to a study, a related study on all American adults, a study that in principle brought in American women or other categories. So here's the deal. Basically, maybe this is the spread among American men, okay? Maybe this is the spread among all American adults, perhaps men and women and other categories. Now you might say, well, hold on now. Will this really be appropriate? Well, yes, in the sense that if this represents the smaller spread for American men, and if this represents the larger spread for all American adults, well, if anything, this is likely to be bigger, right? The spread among all American adults is likely to be larger, which then would lead to a conservative estimate for the required sample size, little n. Remember, the general principle here, in terms of being conservative, is that when in doubt, raise the sample size. To make sure we're not sued, to make sure we don't end up with unsatisfactory results, try to raise the sample size. Now, you may not have the money to explode it out to 1 million or something, but be reasonable. So basically, when in doubt, sigma could be a bit larger. Our estimate for sigma could be a bit larger to make our estimate for the required sample size n a bit bigger. It's okay if our estimate for sigma is a bit bigger. If our estimate for required n is a bit bigger, we're being conservative. Within reason. Don't waste anybody's money or time. Okay. Again, being conservative means erring on the side of making n larger than it needs to be. So for example, sigma might be a bit larger than it needs to be. Or we could begin sampling. Let's start our sampling right now, all right? And use the running value of S sometime after the sample size gets past 30. So remember, we start feeling safe after the sample size is past 30, then we don't have to worry so much about normality in the Big Daddy distribution. So let's say that you get a machine to randomly grab 100 cartons of ice cream. Okay, find the sample standard deviation for that sample. Crank it through the formula where you use that value for S, okay, and plug it into sigma. If little n turns out to be 100 or 90 or 80,
then you're done. Then you've done all the work you need. In fact, you're going to get results perhaps even more precise than what's been asked of you. But if n turns out to be, say, 300, then you have 200 more cartons to sample. A purist might say, well, start from scratch, do all 300 in the future. Don't use your pilot sample. That's a matter of judgment. But again, you could use a running value for S, the sample standard deviation, based on a pilot sample. And your estimates could be updated along the way. And then, although this was quite rough, remember the 2SD or 2 sigma rule for estimating a standard deviation. It's like my example in the bookstore. What's your estimate for the realistic range of prices in a bookstore? If we could walk into a bookstore, that could be months from now. And maybe you say, well, I think roughly the books range between, literally range between $20 and $180. That might be on the cheap side. We're just doing an example here. Well, then the realistic range would be 180 minus 20 or $160. So you're saying realistically, if you exclude the weird cases or outliers, the realistic range for the textbooks in a bookstore, again, this may be on the cheap side, but let's say it's $180 minus $20 or $160. Then the realistic range divided by 4 gives us $40. And that could be a ballpark estimate for sigma, very ballpark. Okay. And it's based on the idea that almost everything, it's a general principle that almost everything will lie within 2 standard deviations of the mean. That's the basic principle, that almost everything will lie within 2 standard deviations or 2 sigma of the mean. All right. Next up, let's play with Excel. That basically ends lesson 28 for us. Next time, we're going to deal with a more realistic case where sigma is presumed unknown. But next up, Excel.
Okay, questions thus far. Okay, feel free to put questions in the chat, all right? Let's go on, Excel.
Hi, everyone. Let's do some Excel. All right. So let's go back to our 95% confidence interval for the population mean amount of ice cream per carton. Our example 1 from lesson 28. Okay. So here are the key sample statistics. This was predetermined. The sample size N is 19 cartons. The sample mean, X bar, was 17.2 fluid ounces. Of course, that's determined after we get our sample. You might even use Excel to figure that out. Get an Excel worksheet, right? And then you have 17, or what was it? Sorry, 19 cartons. 19 cartons. You figure out how much ice cream is in each carton. You have these 19 amounts of ice cream, and you can find the sample mean. The sample standard deviation we won't need because we're assuming we know sigma, the population standard deviation. We assume sigma is 2.35 fluid ounces. So on Excel, to find a 1 minus alpha confidence interval using Z critical values, so we're using a Z distribution. Again, we're assuming sigma is known, so we're using Z. So here's the form that we use in Excel to find E, the margin of error. Confidence.norm, that uses a standard normal distribution. Alpha, that's the complement of the confidence level. So if alpha is, so if the confidence level is 95%, all right, then 1 minus alpha is 0.95. That means that alpha itself is 0.05. So we want to use, in our example, alpha is 0.05. The population standard deviation sigma is assumed to be 2.35 fluid ounces. The sample size N equals 19 cartons. So that was all this sample data here. Well, this here is sample data. This is the population standard deviation. That's presumed known. All right. So let's type this in. And this will give the margin of error equals confidence. Can I spell? Confidence.norm 0.05, that's alpha. Sigma, the population standard deviation is 2.35, 19, the sample size. And we get, whether you round off or round up to be conservative, you get about 1.1 fluid ounces to 1 decimal place, like here for X bar. So 1.1 fluid ounces. And then you would get the lower limit and the upper limit for the interval by taking the sample mean, X bar, okay, and then subtracting the margin of error for the lower limit. For the upper limit, you would add the margin of error. All right, so for the lower limit, it's the sample mean 17.2 minus, or you could refer to a cell that had the sample mean, minus the entry in A8. Okay, and this rounds down to 16.1. Well, the thing is, if you're using the margin of error as 1.1, then yeah, 17.2 minus 1.1 is 16.1, right? For something like this, you could round out, meaning you round down the lower limit, you round up the upper limit to be conservative. Don't freak out about that. All right, but yeah, 17.2 minus 1.1 is 16.1. For the upper limit, that's going to be 17.2 plus A8, the margin of error. Okay, and we get 18.3 fluid ounces. Again, 17.2 plus 1.1 is 18.3. Again, if you're playing it conservatively, then you would round out. I would say rounding out, which means you round down the lower limit and round up the upper limit to be conservative. Again, don't freak out about that. All right, so we get the interval from 16.1 fluid ounces to 18.3 fluid ounces. Remember, how is the 99% confidence interval different? It's going to be wider. The 99% confidence interval will be wider than the 95%. Let's check that over here. The margin of error is going to be bigger. Confidence norm. Alpha is 0.01. If alpha is 0.99, sorry, if the confidence level is 0.99, then alpha is 0.01. Same standard dev, sigma, same n. And we get about 1.4. Remember, that was the margin of error we got for the 99% confidence interval, right here, 1.4 fluid ounces, right? So this rounds off to 1.4, or you could round it up. To get the lower limit, you take the sample mean minus E. For the upper limit, is the sample mean plus E, the margin of error. And we get from 15.8 to 18.6, whether you round off or out. 15.8 to 18.6. 15.8 fluid ounces to 18.6 fluid ounces. So we verified that. All right. We'll deal with T distributions later. That's when we don't know sigma. We use S. That'll be later. Okay, so that's how you can use Excel. Granted, if you use something like StatCrunch, StatCrunch will just pop out the confidence interval, but it's good to know where these things come from. And it's good to know how good old Excel can deal with these things. Next time, we're going to deal with the T distributions and what happens in the more realistic case where we don't know sigma, we use S instead, the sample standard deviation. Next time.
Wait, any questions? Because if you understood the ideas for the case where sigma is known, then we can very quickly deal with the case where sigma is unknown. All right, any questions? Feel free to put questions in chat.
Hi, everyone. So we're now going to do the more practical case in lesson 29, where we're estimating a population mean mu if sigma is presumed unknown. This is the more common and practical case. Now, you might be wondering, did I waste your time back in lesson 28 then, if that was the less practical case, where sigma was presumed known? Not at all. I never waste your time. Not at all. Because if you understood lesson 28, and I hope you did, as best you could, then lesson 29 is fairly straightforward, except there are some differences. All right. How do we use T distributions to estimate mu? So we're going to be using T distributions, not the Z distribution, because there's a price to be paid if sigma is unknown. All right. So in this lesson, similarly to before, we will find 1 minus alpha confidence intervals, or CIs, for a population mean mu under these assumptions. And again, the most common confidence levels here, 1 minus alpha, are 95%, 0.95, 99%, 0.99, and in our example, we're going to see a 90% confidence interval, 0.90. Okay, and we're going to assume the following: that the population standard deviation is unknown. That's the key difference from lesson 28. We are finding confidence intervals for a population mean. That's a big predicate to all of this. And again, the central limit theorem has to apply, although we're really applying a variation on this. But again, when does the CLT apply? If the Big Daddy original distribution is approximately normal, or if the sample size is big enough, say bigger than 30. Again, the 30 is not from any algebra, it comes from practical observation. And if the sample size is large enough, then we don't have to rely on normality in the Big Daddy distribution. So again, these assumptions for the central limit theorem, they're the same as before, as for lesson 28, when we handled the Z distribution. Okay, so now, how do we construct a 1 minus alpha, that's the confidence level, a 1 minus alpha confidence interval, CI, for mu, a population mean? Well, when sigma is unknown, is given by the following. This here is the same setup as before. Same as before. The center of the confidence interval will be the sample mean, x bar. We're going to say that the population mean, we believe to be the sample mean, give or take the margin of error, E, the exact same as before in lesson 28. But now there are a few differences in the formula for the margin of error, and that of course impacts this combined formula down here, which you can apply directly. And we're going to use the t distribution on n-1 degrees of freedom, where n is the sample size. Remember that there's only one z distribution. There's only one standard normal z distribution, but we have infinitely many t distributions indexed by the number of degrees of freedom. We want the one on n-1 df, where n is the sample size. This formula may change for different applications down the line in statistics. Now, what are the two differences you see between this formula and this formula that we had in lesson 28? What are the two key differences between this formula and ye old formula from lesson 28 over here? Well, they're both confidence intervals for mu, a population mean. They're both centered at the sample mean, x bar. But in lesson 28, we used a z distribution. In lesson 29, we're going to use a t distribution, namely the one on n-1 degrees of freedom. We still use that alpha over 2 notation. We're still splitting that alpha probability in half, symmetrically between these two tails. That stays the same, the subscript. Also, since we don't know what sigma is, like we did in lesson 28, we're now going to use S. So here are the two key differences from what we saw in lesson 28. Instead of a Z critical value, we're going to use a T critical value over here. For the same confidence level, this will be larger than its Z counterpart. We'll see why. Basically, it's because we're going to end up with a bigger margin of error. Instead of sigma, we had sigma in lesson 28, we're going to replace it with S, the sample standard deviation, because we've drawn the sample by now, over root n. So you can see that this CLT piece is still here, basically, except that we're replacing sigma, the population SD, with S, the sample SD. Again, let's review the two key differences between the lesson 28 formula and the lesson 29 formula.
So again, in lesson 29, we use critical values from a t distribution instead of from a z distribution, instead of from the z distribution. And we're going to use the sample standard deviation S instead of the population standard deviation sigma, because we're assuming sigma is what in this lesson? We're assuming sigma is unknown this time. Oops. Now, unknown. So we're stuck with S instead of sigma. But we pay a price for that. Because we're using S instead of sigma, that throws more uncertainty into our analysis. It throws a wrench into our analysis because the CLT wants us to use sigma. Well, we don't have sigma, so the best we can do is use S, the sample standard deviation. The price we pay for that is that we have wider confidence intervals because we're using critical values, CVs, from a T distribution as opposed to the Z distribution. And for a given confidence level, the positive T critical value will be larger than its counterpart Z critical value. Now it's true, however, that as a sample size gets bigger, if N gets very large, then the number of degrees of freedom, N-1, gets very large for the T distribution, and you get something close to a Z value. So if you have a very large sample size, then this T critical value will be very close to the Z, and it's almost as if you knew sigma, because S will target sigma very well for a very large sample size. Before we do our first example, remember that the rounding rule will be the same. So we're going to round off this margin of error, E. That's this whole guy here, right? The margin of error is this whole thing over here. We're going to round off the margin of error, E. This is E. We're going to round it off to the same number of decimal places as the given value of the sample mean, x bar. So the same as for lesson 28. So if x bar is rounded off to 3 decimal places, we would round E off to 3 decimal places, or round up. Again, if we want to be conservative, we round up the value of E, the margin of error, to that number of decimal places. By rounding up, that tends to widen the resulting confidence interval, and we're playing it safe. We won't get sued. When in doubt, for a given confidence level, if anything, make your interval a little bit wider so that the actual confidence level is a bit higher. That's our way of playing it safe. So let's go to our example here. We're no longer talking about recalibrating an ice cream machine. That was kind of specific, wasn't it? We can do a more general example now. All right, here's our example 1 for a 90%, in this case, CI for a population mean where the population standard deviation sigma is unknown. We're finding a CI for mu, where sigma is unknown. So let's say that you're a house assessor. You work for a real estate company. You assess house values in the lovely city of Springfield, maybe from The Simpsons. So you go around assessing their value. You want to know how much the average house is worth in the lovely town of Springfield. Well, is it lovely? Okay. So we're going to assess the average. We're going to do some assessing and try to estimate the average house value in Springfield. So who knows? Maybe you go to an old fraternity house. You might see a broken window here, empty beer keg there, maybe some guy lying down there. Then the house may not be valued so much, and that might bring down the property values. But anyway, let's say that the houses in Springfield have values that are approximately normally distributed. What does this assumption allow us to do? It allows us to use what theorem, basically? It allows us to use the central limit theorem, or at least the variation we're going to apply in this lesson. 10 randomly selected houses are assessed. So what is 10? N equals 10. That's the sample size. Oh wait, it's not that big. It's not even 30 or 31. It's a low sample size. It's a small sample size. That's okay. Why is that okay? Because we're applying the central limit theorem. Granted, if your sample size were larger, then we would get better results in some sense. But in terms of our ability to apply the CLT, the central limit theorem, it's sufficient that we have a normal distribution to begin with, even though the sample size is small. The sample mean house value, so let's say that our assessor goes around to 10 randomly selected houses in Springfield, goes to an Excel worksheet, types in the 10 values for these 10 randomly selected houses in Springfield, takes the sample mean, and we find that the sample mean for these 10 house values is $350,000. And we can ask Excel to find the sample standard deviation, which is $25,800. You might remember an old spreadsheet that we had. I wonder if I still have it. There was an old spreadsheet I had where I showed you how you could find the mean and standard deviation. Okay, like over here, all right? So here's the sample mean, right? If these are 5 sample test scores, here's a sample mean. It's just the straight average function. Here's a sample standard deviation. Treating this as sample data. It's important we treat this as sample data. So sddev.s, we get the sample standard deviation. All right. Anyway, the assessor does that in his or her Excel worksheet or StatCrunch, whatever. And we're now going to find a 90% confidence interval for the population mean house value in Springfield. This is mu. When you write your final interpretation, right, then you should say the population mean house value in Springfield. As a shorthand, we'll use mu, the notation. And we're going to write the confidence interval in both this form involving the margin of error and also the form involving the limits. And we'll interpret. All right. The sample size is 10. Because we don't know the population standard dev, we're going to use the sample standard dev, S. I'll put that in red, bright red. This is S. We're going to use a sample standard deviation. So we're going to use the T distribution, not the Z distribution. On how many degrees of freedom? Not 10. It's n minus 1, remember. N minus 1 degrees of freedom. If n is 10, n minus 1 is 9. So we want the T distribution not on 10 degrees of freedom, but on 9. You're going to use these hints. Basically, the positive critical value that we're going to plug in from this T distribution on 9 degrees of freedom is going to be 1.833. If you compare these critical values to the corresponding critical values from a Z distribution, from the Z distribution, if you're doing a 90% confidence interval where the Z distribution is involved, then your positive critical value is positive 1.645. Notice that the positive critical value here for the same confidence level, 90%, I got to compare apples to apples. Notice here the critical value for this T distribution, 1.833, is a bit higher. In general, for the same confidence level, this positive critical value for a T distribution on any number of degrees of freedom, this would be higher than this Z value over here. Although as the number of degrees of freedom gets large, as it approaches infinity, this will get closer to the 1.645 from Z. Anyway, that was some theory. Again, it's good to state what mu is. Mu is the population mean house value in Springfield. The methods of this lesson apply because, first of all, we're finding a confidence interval for mu, a population mean. We're assuming that the population standard deviation sigma is unknown. So we're using lesson 29, not lesson 28. We're using a T distribution, not the Z distribution. There's more uncertainty here. Because sigma is unknown, we resort to using S, the sample standard deviation, and that throws a wrench in, that throws in more variability. The CLT applies because we assume the house values were normally distributed in Springfield, approximately. So it was okay that the sample size 10 was rather small. We're relying on the Big Daddy distribution being about normal. Okay, again, the sample size n equals 10. That means that we're going to use the T distribution on 9 degrees of freedom. We're also going to plug the 10 into
here, this radicand. The sample mean X bar is $350,000. The sample standard deviation, we need that this time. We assumed it was $25,800. That was from the Excel spreadsheet or StatCrunch. Okay, so the margin of error, this is from the formula I showed you earlier. The positive t critical value, that's from the hint. For a 90% confidence interval, t distribution of 9 degrees of freedom, we want the 1.833. That's the positive critical value we want. That goes here, the 1.833. The sample standard deviation from our Excel spreadsheet was $25,800. Sample size was 10. The 10 goes here, not the 9. Work this all out, we get about $14,955. We'll show how Excel can spit this out for us later on. So a 90% confidence interval, this is the margin of error for a 90% confidence interval. For a 90% confidence interval for mu, we take the sample mean, which was the $350,000. We take the sample mean, we plug that in here. The margin of error, put that in purple, the margin of error is about $14,955, all right? Well, we calculated up here. It goes here. Okay, U is about $14,955, that goes here. So this is one form for the confidence interval. We're saying that the population mean with 90% confidence, this population mean is about $350,000, give or take about $14,955. Okay, what if we actually want the limits of the interval? For the lower limit, we take the sample mean and subtract E, so we take the minus case, we get the lower limit, $335,045. For the upper limit, that's the plus case, the sample mean plus the margin of error gives us $364,955. The lower limit goes here, always. The upper limit goes here, always. Separate them with a big comma. Interpretation. We are 90% confident that this interval here contains the basically mu, but you should write it out for the layperson, contains mu, which is the population mean house value in Springfield. We're 90% confident mu is somewhere in here. So in the mid 300,000s, basically, in dollars. All right. And again, see, this interval is a bit wider than it would have been if we had used the z-distribution because, see here, we're assuming that we don't know sigma, so we have to use S, we have to use t critical values, and that leads to a bigger margin of error, so this interval is more spread out. Okay, later on, we're going to talk about tests for other parameters besides mu. In our next video, I'll show you how to use Excel to come up with these things.
Any questions? That's the end of the concepts really for today, and you can do the homework through 29. I do have the Excel bit, and I want to show you something really good afterwards that's on my website.
Hi, everyone. Let's do this house assessment example on Excel. So we have these 10 randomly selected houses. We find that they're, so N is 10, right? And we find that the sample mean is $350,000 and the sample standard deviation is $25,800. And we want to find a 90% confidence interval for mu, the population mean house value in the lovely town of Springfield. Okay, so here's our key information. Excel will know that it needs a t-distribution on 9 degrees of freedom. So we just need to input the sample size, not the number of df. All right, so on Excel, to find a 1 minus alpha confidence interval using t critical values, CVs from a t-distribution. Okay, to find the margin of error, here's the form, confidence.t. Remember, it was confidence.norm for the z-distribution, confidence.norm. For the t-distribution, it's confidence.t. All right, alpha here is 0.1 because if we're dealing with a 90% confidence interval, if we want to find a 90% CI, right, 1 minus alpha is 0.90. So alpha itself is 0.10 or 10%. It's this picture over here where we want a 90% confidence interval, 0.90, and we have 0.10 total, that's alpha, total in the two tails. That's left over. Okay, so alpha is 0.1. The sample standard dev, S, is $25,800. Sample size N is 10. We should get the margin of error equals confidence.t. Alpha is 0.1. S is $25,800. N is 10 houses. And we get, if we round off or up, to be conservative, $14,956. In my notes, I used $14,955, maybe because of round off error over here. Okay, so then for the lower limit, remember the sample mean was $350,000. We subtract the margin of error E, which is highlighted in gray here, cell A8. The lower limit is that, upper limit, we take the sample mean and add the margin of error. Okay, so we have here from 335,044 to, whoops, yeah, okay. And then over here equals. Okay, so from $335,044 to $364,956. And that's what we get here. We're off by $1 because of the whole rounding thing, round off error thing over here. But don't freak out about that. If you're off by $1 here or here, I'm fine. I think we have a pretty good idea of what's going on. We are 90% confident that this interval contains the population mean mu. If we're off by $1 here or there, that's okay. So that was Excel. Next up, we're going to find confidence intervals for P, sigma, and sigma squared, other parameters, not just mu. We've been dealing with confidence intervals for mu, a population mean. We're going to deal with confidence intervals for other parameters later on.
Okay, and I want to show you a couple of things, actually. One is based on my website. Go ahead and copy paste this. Bring up, let's do this. Okay, on my website, I have the formula sheets. Okay, I don't know if I've pointed these out before, but for example, formula sheet for quiz 4, this is where they come in really handy. Okay, so when on campus, when my students would take exams, I would hand this out beforehand. But this is a summary of formulas that you see throughout the various lessons on a couple of pages. So if you wanted a couple of pages, well, here I guess 3 pages. Yeah, 3 pages with the various formulas for the lessons, so you don't have to keep scrolling through the notes. The formula sheets are on my website. Okay, under formula sheets. All right. Also, I hope I have the stat calculators. Hold on, let me see if I have the stat calculators here. Yeah, tutor homework, right. Okay, so for tutor homework, I don't think I mentioned the t-distribution. So for example, what do we have? We had a 90%, it was a 90% on 9 degrees of freedom, right? So we want 90% in the middle, 0.90, okay? And then 9 degrees of freedom, voila, 1.833 is the t-value. So if you find Excel not very user-friendly, well, tutorhomework.com will at least give you the hints that I give you in the homework. All right. And we'll usually be using the middle piece over here, although later on for hypothesis tests, we might use these other ones, left tail, right tail, and two tail. But for right now, we're doing the middle. All right. So any questions? Later on, we're going to talk about, I guess, standard deviation and variance, and also P. Any questions? Any questions? We're done through lesson 29. Lesson 29. Okay. Yes, I'm glad I finally mentioned. I remembered them. Right. So we have the formulas on a few nice sheets. They're meant to be study sheets. Basically, I hand them out on exams, but I think they'll help you even with the notes available to you. It's good to have them summarized. Okay. All right. So it's well, I'm on time actually. Okay. I could have played more videos, cute videos. I'll do those later. Any questions? Any questions? Oh, by the way, I guess for Canvas. So what is Canvas for? I'm getting the sense that students use them for grades, sort of the weekly plan. I don't know if you use it for net tutor or class discussion. All right, Winston was saying that the class discussion wasn't used that much, but yeah, I am thinking about using Canvas more maybe next semester, and I'm getting the sense these are the key applications. But let me know if there's anything else I can use, even for this semester, maybe. I know a little bit of Canvas, not much. Any questions? Any questions? Anytime you have any suggestions for me or the class, let me know. All right, you guys can make improvements this semester or next semester. All right. Anyway, we're at 9:36 basically. So let's stop here, but I'll take questions. Okay. Have a good night for many of you. We're done through lesson 29. Okay. Okay. But right now, I'll take questions if you have any. Mute again. All right. Okay. Thank you all. Any questions? Any questions? And again, feel free to give me any advice or suggestions regarding the class or Canvas or anything. Any questions? Okay, so I'll come back at 9:40. Be back at 9:40. And if you have any questions, let me know. And don't forget to change your timepieces by an hour. I didn't change my watch. Okay, I'll be back. I'll pause for now.